No, but there's only like going back and forth. Like, oh my gosh, it's like but so what I'm supposed to do and then the same. Oh my God.
Let me go over the calendar for this week. First, I misnumbered homework 4. So homework 4 will start with today's homework. So this week, no assessments. We're just going to go back to the very beginning of first semester, and some of these topics we haven't seen in a while. So we'll spend today going over limits and continuity. Tomorrow we'll do differentiation. You've seen a lot of topics for differentiation, like product, chain, quotient. We've seen that even as we're doing second semester topics. So this should feel more familiar. Related rates, we haven't seen that in a while, so we will spend a day doing that. Extreme value theorem, mean value theorem rules. We kind of got a taste of it with the last quiz, but I still want to devote a day to it. And then Friday, curve sketching, derivative graph, particle motion. We'll spend a day on that as well. So these 5 assignments will go in the gradebook as a quiz grade, and Friday's homework I'll check after spring break. Okay. I may be sending out text reminders to some students individually to ask if you want to do the chapter 5, 6 test recovery. If you do, you have to come in and do test corrections and take the chapter 5, 6 test. I'm not committed to that Tuesday date. If you feel like you want some extra days to review for it, but ultimately, if you want to take that test recovery up to 79, then I need that test to be made up by this Friday. Now, if you want to take it sometime later, you can, but then the highest that you can get is a 70. Okay, so if you want to take a recovery up to 79 for that chapter 5, 6 test. Now the chapter 7 test, Most of you guys did pretty well on that. I will hand that back to you sometime later this week. And for those students who wanted to recovery on that, that will happen the week after we come back from spring break. Okay. Okay. Any questions about the calendar? All right. Let's look at limits and continuity, page 1. Okay, so let's review what limit is. A limit tells us the y value that a function approaches from both sides as that function's x value gets closer and closer to that number. So the key word here is approaching. Okay, we don't really care what's happening at that point. We just want to know if I pick points on either side of my target, is the graph headed towards the same destination? As long as it's headed towards the same destination, that's enough for us to say that there's a limit. There could be a hole there. The point could be defined somewhere else, but it's not going to impact us. Okay, we care about the approach more than what's happening at that particular location. So a quick example here before we get to the ones below. Let's say I had a graph that looked like this. Here, if I asked you for the limit as x approaches 3, we see there's a hole. We see the graph is located somewhere else, but the limit is asking where's the graph approaching from both sides of 3. So there's 3. I'm going to pick points on either side of 3. I'm going to just draw an arrow along the path towards 3. Notice that both arrows are directing me towards a y value of 1, and that's enough for me to say that's where my limit is. Okay. I look at the arrows and I look to see, okay, are the arrows pointing to the same value? Okay, if it's pointing to the same value, that's the limit. We don't care about the fact that the order pair is up here. That's something else, right? If I asked you f of 3, then you would tell me 4, but the limit is more about the approach than the physical location. Okay, let's look at number 1. Limit as x approaches -3. So first thing we do is we pick points on either side of -3. Here and here. Relatively close. And now I'm going to draw an arrow along the path of the graph towards -3. Okay. Are the arrows headed towards the same y value? Yes. And where are the arrows headed towards? I have it right around 2. Does it look a little bit under 2? Okay, that's fine. If you say 1.9, that's fine. But I have it right. Yeah, so I meant to have it right at 2. So even though the y value is located at a different place, we're looking at the arrows to kind of help us determine where the limit is. Okay, number 2, f of -3. Now this is telling us we're just looking for the point, right? So what's f of -3? 1. Okay. So you see that distinction here. Limit is about the approach. Order pair is about that physical point. Okay, number 3, limit as x approaches -3 from the left side of -3. So now there's a separate notation there that indicates we're only looking at the branch starting from the left side of -3. So we're just looking at this branch. Okay, so where is this headed towards? 2. Okay. Limit as x approaches -3 from the right side of -3. That means we're only following what this is telling us, and this is telling us what? 2. This is what we call one-sided limits. It's not the true limit. It's just, its job is just to tell us what's the behavior from just one side. Now, the connection with this versus the true limit is that if your one-sided limits are in agreement, then that's where your limit is. If your one-sided limits are not in agreement, that means your limit does not exist. Okay, so this is kind of a more detailed way of breaking down how we approach limit, right? We always look at it from both sides, and we're essentially, when we do that, we're doing one-sided limit twice, once from the left and once from the right. Okay, number 5, limit as x approaches 0. So again, if you see a limit notation, that means you got to check it from both sides. So I'll pick points on either side of 0. Are the arrows pointing me to the same y value? No. So this is where we say the limit does not exist. Okay. For number 6, what about f of 0? Yeah, now you're looking just for what's happening at 0. We don't care about anything else. We see there's a hole there that's not defined. The defined value is 2. Okay, so see if you guys can fill out 7 through 12. Let me see how you guys do with that. And let's see how we did here. Limit as x approaches 0 from the left side of 0. That means we're just paying attention to the arrow, where the arrow is headed towards from the left side of 0. We see it's headed towards a y value a little bit under 1, so you can say either 0.9 or 0.8. Make your best estimation. That's good enough. Approaching 0 from the right side of 0, we see the arrow is headed towards 2. So we see how these are not in agreement. And that just kind of further establishes that is why the limit doesn't exist, right? We don't have an agreement of the arrows, and so this is the reason why the limit doesn't exist. Okay, number 9, the limit is 1, the order pair is 1, the one-side limit are also 1. So this is telling us something about the graph as well. Do you guys know what do we call it if the limit exists and the order pair exists and they are all in agreement? That means the function is what? Yes, continuous. Okay, so we're going to see that on the next page, that this is part of the condition for function that's continuous. If the function is continuous, then you're not going to see any distinction between limits and order pair. It's all going to be matching up nicely. Only when there's a hole or asymptote are you going to begin to see some variations between limits versus order pairs. Okay, but otherwise, if it's a continuous function, your limit, your one-side limit, your order pair, they're all going to tell you the same thing. Okay, any questions? All right, let's go to the bottom half. Here's a review of evaluating limits algebraically. So we have two categories. One is where we're approaching a real number, limit approaching real number, and then another category is limit approaching infinity. So let's talk about the real number first. Okay, so if your limit is approaching a real number, we always plug in that x value first. Okay, make sure that you plug in the x value, the whole number x value. Do not do anything with decimals, even if you see one-side limit. If you see one-side limit notation, just completely ignore it. Okay, you're just focused on that whole number. Don't let the one-side limit throw you off. Okay, so you plug in that whole number, and number two, you look to see what is that going to give you. Okay, a couple of things can come out. If it comes out as a real number, then you stop. You have the limit, you have the answer, there's nothing more to do. Now, if you get 0 over 0, okay, make sure that you don't, if you see 0 over 0, don't just stop there and say that the answer is 0 over 0. Okay, so that's one thing that you want to do. Also, 0 over 0 is not the same thing as limit does not exist. Okay, if you see 0 over 0 is indeterminate form, and indeterminate form from an algebraic perspective or graphical perspective, that means there's a hole in the graph. If there's a hole in the graph, we know the graph doesn't exist at that point, but the limit still exists, right? We saw that from the previous example that if there's a hole in the graph, your limit can still exist. We just have to go ahead and find that. So if you see 0 over 0, understand that there isn't a real number answer waiting for you at the end of the problem, but you haven't reached it yet. So there's a couple of options that we can do. We can either factor. If it's a radical, we can go through conjugate method. If it's a complex fraction, we can simplify it. Any of those options, if we can apply those methods, we can then reevaluate the reduced expression, okay, and see if that gets us a real number. Now, if you get 0 over 0, there's another option. And this is the one that I think a lot of students prefer. And that is using L'Hopital's rule. As long as you can find the derivative of the top and the bottom separately, you can evaluate the limit. And you don't have to go through a specific method for each type of problem. You can just handle it all using L'Hopital's rule. Okay. But sometimes it's good to know some options available just so that you can either double check your work or, it's nice to have some options to choose from. Now, we know what to do. We know what happens when we see a real number, we stop. If we see 0 over 0, we keep working until we get to the right answer, until we get to the real number answer. But if you get 10 over 0, that's telling us that the limit does not exist, okay, because there's a vertical asymptote there. Okay, it could be 10 over 0, it could be 3 over 0, it could be 5 over 0. Okay, that's a visual indication that there's a vertical asymptote. And if it's just asking for the limit, you would say the limit doesn't exist. But if it's a one-sided limit, then you do additional tests using decimals. Okay. Because if we're approaching an asymptote, there's only two options, right? Either the graph is headed towards positive infinity on one side, or it's headed to negative infinity on the other side, okay, or vice versa, right? Okay, so let's look at some of those examples approaching real number before we look at the infinity ones. Okay, so example 1, what's the first thing we do? plug in 3, just 3, right? No 2.9, no 3.1. We don't do any decimals. We just do the real number. Okay. Basically, ignore the one-side limit. It's tempting you to try something else, but you're not gonna. You're just going to go through the process and work with that real number. Okay. So 3 goes in first. And what do we get? Okay, 0/0. So understand that this is incomplete, but it does give us something to work with. We know that there's a whole, we know that there's a real number answer. We just have to find it. Okay, so here, let me go through 2 options. One option is you can factor. You can look for the whole, remove the whole, and then reevaluate. Let's try that first, and we can do another option, do another way of looking at this. Okay, so factoring, the numerator is not going to change. The denominator multiplies to be -3, adds it to be -2. Okay, do you see a common factor? Yes, right. X minus 3 goes away. There's a 1 left over. I reevaluate, and what do we get? 1/4. That's a real number. That's our answer. Okay, I want to explore another option to do this problem is going through L'Hopital's rule, right? As soon as you see 0/0, that gives you the green light to apply L'Hopital's rule. So L'Hopital's rule says, take the derivative of the top. What's x minus 3's derivative? 1. What's the derivative of the bottom? 2x minus 2. Okay. As soon as you find the derivative once, you're going to reevaluate. Okay. So reinsert 3 for x. Again, no decimals. Reinsert 3 for x. 3 times 2 is 6. 6 minus 2 is 4. 1/4. We get same answer both tries. Okay, any questions with one? Okay, number 2. First things first, what do we do? Just -3, okay? Just -3. We get -5/0, so this is telling us something different than 0/0. What is this telling us? Physically, what's happening at that point at -3? There's a vertical asymptote. So you know that the limit doesn't exist at an asymptote. However, we go back and we look at the problem. Is this asking for the true limit? It's only asking for the behavior from the left side. So here we can't say limit doesn't exist. True, the limit doesn't exist, but it's only asking for how is the graph moving towards the asymptote from the left side of -3. Now we play with decimals, okay? Until we realize there's an asymptote, the decimal is not going to do anything for us. We're just completely ignoring the fact that it's a one-side limit until we realize that there's something additional that we have to provide. So now we can choose a decimal value. So what can we test that's to the left of -3, but also pretty close? Yeah, -3.1. And all we care about is whether is the graph headed towards positive infinity or is it to -infinity? We're just going to test and check the signs. And typically, if you see this problem on the AP exam, it'll be part of a non-calculator section, because if you had a calculator, you can just plug it in. But this is one where they would test you on whether you can evaluate it from an algebraic perspective. Okay, so let's test, put -3.1 in for x. Okay, the numerator gives us positive or negative. Negative. Denominator also gives us negative over negative is positive, so we know it has to be positive infinity. So we know that as we approach -3, the graph must be headed up. Okay, take a look at number 3. What's different about number 3? Compared to 1 and 2. Okay, it's approaching infinity. We have a different set of rules for infinity. Okay, so for infinity, if you look at above here, we don't plug in that value. We start comparing degrees. Okay? And we look to see which side has the higher degree. If the numerator has or if the numerator is lower than the denominator, if it was like x squared over x cubed, if the denominator has a higher degree, then your limit is always going to be 0. If your numerator and denominator have the same degree, then you just look at the ratio of their leading coefficients. It'll be a fraction. If your numerator is more than your denominator, then your limit doesn't exist, but then you'll test like a large value to see where is the graph headed. You know, as it exits the graph, is it going up or is it going down? Okay, so we see negative infinity. We want to pick out the highest degree. What do you notice between the numerator and the denominator? Same or different? Same, right? They both have degrees of 2. So we simply take the ratio of the leading coefficient. What's the limit going to be? Yeah, 1 over -5, which is the same thing as -1/5. Okay, number 4. We're back to a real number. So insert 0 in for x. First thing we do, right? See what happens. Okay, sine of 0 is 0. 2e to the 0 is 2. 2 minus 1 is 1. Natural log of 1 is also what? Also 0. Okay, this tells us that there's a hole in the graph. The limit does exist. We just haven't found it yet. But there's only one method to handle this. We got to use what? Yeah, we got to do L'Hopital's, right? We cannot factor. There's no conjugate. There's no simple. There's no complex fraction to reduce. We're forced into L'Hopital's for this problem. So we take the derivative of the numerator. And I have some reminders below here. Sine's derivative is just cosine. Natural log of u becomes u prime over u. So my u value is what's inside the parentheses here. So 2e to the x minus 1 becomes just 2e to the x over 2e to the x minus 1. So as soon as we find that derivative, we can go back to reevaluating. Right? So replace every x with 0. Cosine of 0 is 1. 2e to the 0 is 2. 2 over 1 is 2. 1/2 is our limit. right, any questions here? Okay. The next topic from chapter 1 is continuity. Okay, so continuity condition says this. First thing we do, so continuity just means that is the graph connected all the way through with no holes, no asymptotes? So obviously you can look at a graph and tell if it's continuous, but algebraically and through calculus, we have to make sure it passes all three conditions. Okay. The first thing we do is we look to see, does the point even exist? So let's say I had a C value here. Okay, we look at the graph, the point exists, great, then it passes the first condition. Okay. Second condition, does the limit exist? So is the graph headed towards the same y value from both sides? And let's say this graph looked like this. We would say the limit does exist because if I pick points on either side of C, my arrows are headed towards the same location, destination. So for this graph, first condition passes, second condition passes, but what about the third condition? Does the limit match where the order pair is? Does not, right? So for this case, this one would fail because the third condition just says, take the result of the first, take the result of the second, and see if they are in agreement. If they are in agreement, then yes, you're good. If they're not in agreement, then we have to say the limit that the function is not continuous. Okay, so for this graph, it would fail the third condition. Okay, so let's look at number 1, where we have to kind of go through the conditions algebraically and without the use of a graph. All right. Function f is defined by f of x between -5 and 5. Let g be the function defined by g of x. Piecewise function, it's f of x between -5 and -3, and it's x plus 7 between -3 and 5. Is the function g continuous at -3? Use the definition of continuity to explain your answer. Okay, so let's go through our conditions. The first condition is, does the point exist? They tell us the x value is -3. So we just want to decide how we can find g of -3. Okay, so g of -3, where's -3 defined? Is it defined for the first piecewise or for the second piecewise? Okay, first one, right? Because it says x is less than or equal to -3, but -3, it's outside the interval for the second piecewise. So we're going to just enter in for f of x. F of x is defined above, so we'll just enter -3 in for root 25 minus x squared. Okay, 25 minus 9 is 16, and root 16 is 4. Passes the first condition. Second condition is the function, does limit exist? Now notice that you have two different functions on either side of -3, so we can't rely on just one limit statement. We need to rely on two limit statements because we have two different graphs on either side of -3. So we'll do limit as x approaches -3 for the left for f of x. Which is the root 25 minus x squared. Again, the one-sided limit is just to indicate which direction we're headed from, but algebraically, we're just going to plug in the whole number, right? So no decimals, right? We never do decimals until we plug in the whole number first and then realize that there's an issue. Okay, so 3 in for x, 25 minus 9 is 16. So again, root 16 is 4. All right, let's look at the limit from the other side of -3. And now we're looking at the x plus 7. -3 plus 7 is 4, so we have an agreement. Both arrows are headed towards the same y value. We know the true limit does exist. So we got through the first two conditions. And now how do we do the third condition? Yeah, compare the first and second, right? Are they in agreement? Yes. So we know the third condition will also pass. Sorry, pause it for. So all three conditions pass. We can say, therefore, all right, number 2, if the function is continuous for all real numbers and if f of x is equal to x squared minus 4 over x plus 2, find f of -2. So x doesn't equal -2. What that means is that f of x exists everywhere except at -2. So we're trying to force a scenario where this function can be continuous. So let's just go through our conditions and see where it breaks down. If it breaks down, we can kind of fix it. Okay. So f of -2. They say it's not defined at -2, but let's just see what happens if we do plug in -2. If I plug -2 in, I get 4 minus 4, which is 0. -2 plus 2, which is 0. 0 over 0, we know the order pair doesn't exist. So we know we have to kind of redefine it. But we don't know where to put it yet, right? Let's figure out where the limit is. And then we have a better idea where that hole is and how we can fill it. So let's go to our second condition, which is evaluating the limit. Notice that this function is not split like the previous problem, right? Previous problem, it was split on that boundary. So we kind of had to look at it from both perspectives. But there's only one function here. All we need is one limit statement. Okay, insert -2 in for x. We already know we're getting 0 over 0. So you have two options, right? Well, first step, you don't want to say the limit doesn't exist. Right? That's not true. Second, 0 over 0 is not the final limit. We have to keep going. So you have two options here. Either you can do L'Hopital's rule, or you can factor, reduce, and reevaluate. So I'm going to factor, but you can do L'Hopital's rule, and you'll get the same answer. Okay, x plus 2's cancel out. Reevaluate. I get -4. So the limit is at -4. So how can I redefine f of -2 so that everything matches nicely? We can fill in that hole where that location is, right? So if f of -2 equals -4, then everything will work out. All three conditions will pass. Okay, last problem here, intermediate value theorem. This says that if a function is continuous, we can guarantee a specific y value on the graph if one endpoint is below the y value and the other endpoint is above the y value. So if you're looking for a y value and you know the graph is connected, as long as one endpoint is below and the other endpoint is above, you know the graph has to cross through that target y value somewhere between. So number one, it says, let f be a continuous function on the closed interval from -3 to 6. So we know it's continuous, so we know there's no surprising gaps in the graph. Okay, f of -3 equals -1. It helps if we just sketch the graph out. F of 6 equals 3. And the graph is continuous, so I'm just going to create a pretend graph. I don't know what it looks like, but I do know that this could be a possibility. Okay, so it guarantees that, and let's just see if we can eliminate the wrong options and be left with the correct one. Okay, true or false, f of 0 equals 0. Okay, the graph I drew doesn't have that, right? So we can't guarantee it if I can create a scenario that doesn't match the option here. F prime equals 4/9 for at least one value between -3 and 6. Intermediate value theorem does not do anything with derivatives or slope. Okay, this is slope related. It's only asking, IVT is only going to tell us a specific, if we can guarantee a specific y value, nothing about slope. So IVT has nothing to do with slope. That's mean value theorem, okay? The y value has to be between -1 and 3 for all values between -3 and 6. Is that a true statement? Sort of. The way that this is saying is it restricted to just between -1 and 3? This is saying that it's restricted. So is it possible for the graph to fall above or below my endpoints? It's possible, right? Maybe my graph looked like this, right? And if it does, then I'm proving this wrong, right? Not for all values. Okay, f of c equals 1 for at least one value between -3 and 6. Okay, so that we can guarantee. Between -3 and 6, the y values is one is below 1, the other is above 1, so it has to cross 1 somewhere between. F of c equals 0 for at least one c value between -1 and 3. Now, it's possible, but we can't guarantee it. Also, -1 and 3 are not the endpoints, so we can't guarantee that. It's only d. Okay, your homework is pages 3 and 4, but I'm going to be checking pages 1 through 4 tomorrow. Okay. Okay, thank you. Yeah, you can do it anytime this week. Yeah. Yeah, take the quiz first. This you can wait till like Friday if you need to. Yes, you can come in anytime. Have a great day, guys. See you tomorrow.
I don't think she's done that. Or thank you.
Okay, see you.
Like, I'm like a new
Thank you.
So, on this one question, I noticed you used, it said to use FFTC, but I don't understand. Wouldn't you just test the endpoints? I don't understand why you would use FFTC.
Because we don't have the FFX graph in front of us. We have to get to the FFX graph.
Oh, so we use that
We have to use
in
that.
order of it.
We'll take it tomorrow right away. So can I just let you know that?
That's fine. Yeah. Oh, when are you taking the quiz?
First period.
Yeah. Dylan, we can take that quiz. For one. It's just part of the circle. So you don't remember it. I'll go back.
You get the rockets.